All right. Hey, everyone. Thank you a lot for coming out and joining us. My name is Boris Jonica. As Rich said, I'm on the data pipeline team here at Yieldbot. And in today's talk, I'm pretty much going to be going over kind of the kind of experimentation we've been doing with GraphQL and using it as a means of exploring time series metrics and just like joining it with our business data and seeing how good of a fit that is. So I'll be digging into schema design for building a language on top of GraphQL for doing aggregations over time-based metrics. And I'll go over how it compares to more traditional RESTful approaches and really discuss the client-server, server-to-server, server database interactions that come along with GraphQL. So first, let me get kind of like an idea of how many people here have heard of GraphQL outside of this meetup, and how many have used it at their company. All right, so like a couple hands, barely. All right, so that's great because I'll be doing an introduction of GraphQL as well before we dig into too many of the details. There we go. All right, so the background. The reason we started doing this is we had a lot of APIs that are targeting delivering metrics to users from different sides of a marketplace. So we have both buyers and sellers of a market, and they have different ways of thinking about performance data. When an ad buyer looks at a data hierarchy, they see it in a completely different perspective from a seller. And in addition to that, we have like a very large pool of data with many cross-cutting dimensions and very complex relationships between the different documents. And ultimately, we end up with clients and product people who really want to be able to dig in deeply and explore these data structures from their own perspective. And oftentimes, it's really difficult for like our server API developers to keep up with the needs of every different client's mental model of the data. And really what usually happens is we expose an API for getting metrics. It serves a need, and then clients want to see what other connections there are. How does, say, a salesperson or a campaign relate to another object? How do we break it up by time? And how do we connect it to our other objects in the database? And as these needs continue to grow on top of existing APIs, using like a RESTful approach tends to become heavier and heavier as we try to like accommodate one aggregation for one user. And say one client wants to get campaigns by or salespeople or cars or something sold by date and by agency or by salesperson, and another user wants to get it by minute in a different aggregation order. And really, like, it becomes difficult to stay true to the RESTful sense of accommodating a whole lot of different custom aggregations, different orders, and different levels of nesting, and still write something useful that isn't just straight up here. Go ahead, use the database, have a free reign, do whatever you want. And we definitely don't want that. So I kind of started researching what the architectural landscape is when it comes to building really product-focused metrics APIs. By that, I really mean something that's highly flexible of the ways that they can aggregate over time-based documents, but also really focused on the higher level needs of a product or a front-end application. I mean, like, we see a lot of these different data stores and technologies coming out of nowadays for working with time series data that tend to be focused more on the infrastructure side of things, on monitoring, on alerting with time-based indices, and really, like, on the API landscape, there's not. I feel like we haven't moved as far ahead for something that front-end consumers can use. Yeah, so then I ran into GraphQL, which had a different way of looking about data. First of all, GraphQL is essentially a query language, a strongly typed query language for existing APIs. The benefit of it being strongly typed, you really end up with highly descriptive error messages for the queries you're writing earlier on in your development process before you even submit a query to the server. And there's a lot of tooling that comes along with that to help clients kind of guess their way to the right type of query on their first attempt, rather than trying to dig through a whole bunch of different sources for documentation and trying out different ways of accessing a field and finding out what works and what doesn't. Fundamentally, GraphQL models its queries in a hierarchical manner. On the server, you describe schemas that describe the relationships that your different objects have with each other. And you present the schema to the client, and the client is then able to start kind of digging in at some level of this hierarchy and get exactly the data that they want out of it without getting any more or any less. And because the clients also like define their queries rather than having the server expose specific routes and dictating, this is how you access this object, this is how you list a set of cars or whatever your business object is. With the client defining the query, the server remains responsible for ensuring that it respects the schema that it's putting forward, and parsing that query and turning that into the various database or dependent service directed API calls that previously the client might have been doing with a RESTful approach, and now kind of it's offloaded to the server to let the server figure out how to bring these related objects together and kind of leave all the application level joining overhead out of the client's needs. And really, like when a client defines a query, it also defines the data shape and the contents that follow the data shape, and the contents end up following that data shape. As a client, you'll always know exactly where the field you're asking for exists and that it exists, and there's nothing else there. And really, one of the couple of the biggest points of it is the introspective facility. If you've ever used if you've ever explored GraphQL and run into a tool called GraphQL, it makes use of the introspective nature of the GraphQL schema, where you can query a GraphQL server itself to get back a schema. And as a client, you can build tools on top of that for auto-completion, for client-side validation that matches exactly the sort of server-side validation that's going on. And really just leads to a landscape where at the compile time, you get a lot further ahead to writing correct code than you would have otherwise. And something that's not mentioned a lot in this discussion is the documentation aspect of GraphQL schema. Along with the introspective nature, along with getting the structure of the data, you also can request as a client the associated documentation with every field and the overall API and query that you're asking about. So let's run through an example of a REST-based example. Say we have a UI that needs to report on the sales of its agents, of its salespeople. So you have, as a backend developer, you're gathering requirements, and you start exposing routes for each resource based on what the UI needs to interact with one by one. You've probably seen this pattern if you've worked with REST APIs in the last 10 years. You get some kind of an endpoint up for listing the salespeople the client can work with, and it gets back a list of salespeople paths. And now as a client, you're like, okay, I want to present information about this salesperson. So you present endpoints for digging into more detail, figuring out the maybe you want to find out the name, what sales it's had, whatnot. But fundamentally, the goal of this application is to report on actual sales, on performance of this person. So we add another endpoint for getting a specific sale associated with the salesperson. And it comes back. You get the revenue, the date it happened, and a reference back to the salesperson that owns it. And this is all nice and good. Once it's all complete, in the UI, you can aggregate the information into some kind of visualization, probably a histogram. And but like, what happens if the user needs to refine the cuts of data it wants to ask about? Maybe wants to like not get such big blocks of data. Say they only want to get agents with more than one sale. So the server alters salespeople and adds some kind of a filter for let's only get the salespeople with at least 2 sales. And another client later on wants to get the car make and car year of this $42 sale, and apparently it's a 1996 Strada. So the second round of requirements comes in. Okay, you had the filter, you had the extra data. Now, maybe your original client didn't really want those extra fields, but such is life. You could filter those out later on. And if we take a look at how this ends up looking in terms of the client-server interaction, we have the first call to the salespeople path. It's the service, which in turn queries the DB and brings back the IDs to the UI. And the UI then makes 2 additional calls to get to the service, which again calls the database for each of these objects and sends back the information. Then the client gets into the individual sales, and so on and so forth in the REST landscape. So there's, you do a lot of work upfront as a client because you can't fetch the sales revenue until you know what sales, what agents end up owning the sales. You don't know what agents you have access to. So you have to go there first, and in the process, you end up with a lot of redundant data that you only really use to build, to perform a join in your application. Like the ID of your salesperson is not actually relevant to anything that you're presenting to the end user of your application. So yeah, while this example is pretty simple, we can like easily foresee ways that both the data structure will grow beyond the bounds of the original client. Like maybe another user wants to see how much was spent on specific cars, and another wants to aggregate by the car brand by day, while another wants to aggregate by month, by car, by salesperson. So complexity grows, and then you end up with a situation, of course, where what if the UI now has hundreds and hundreds of sales to deal with that it has to aggregate over just to get an end aggregation. Like, okay, maybe you add a flag for including the dependent sales, and at this point it's fetching a lot of data up front, but it's making fewer calls, but I guess you're trading that off with a huge amount of additional data where you don't really need the date or associated salespeople or car make. So it'd be nice if you had a way to filter that out. And what happens then if other users want other related objects? Maybe there's other members on the team of that salesperson, and they want to get all of those salespeople. And so then maybe it's time to write some kind of a DSL in the like query of your route so that you can just be able to like fetch nested objects. Or maybe you go with the way of adding custom endpoints for every need and every product, and you hope that your code on the backend stays dry and modular, and that naming is easy. So hopefully everyone's able to discover what those custom endpoints are and what they do. So you have to keep all your documentation up to date. I mean, all in all, it's obviously not like a bad situation, but there are drawbacks that are worth understanding in the RESTful world, and maybe it's worth examining good job of taking those into consideration and building something was beyond all of this overfetching and application side joining that is very error prone. So let's look at the same query in GraphQL. As you see in the first this query, it looks very JSON-like without all of the quotations and commas for the most part, but it looks like half of a JSON object with just the keys in there. You're asking for salespeople, first name, last name, and yeah, with this approach, you are saving a lot of network costs because you're not making multiple round trips to join sales revenue to the salesperson. You have your filter up in the top level objects, so that functionality is spared, and what you end up getting back is something that looks very much like the data you asked for. So there's really no guesswork involved in figuring out how much revenue Thomas Paine brought to the company by selling cars. So I mean, obviously, we're not just limited to asking about one specific thing. We can have other root level objects in addition to salespeople. It's all about how you decide to define the schema for this. Yeah, at this point, we can add additional fields to our schema without having to worry about breaking existing clients. Because the client specifies exactly the query they want, the structure they want their data in. Additional fields added only affects the clients that actually want those fields. So backing up to the diagram before, we end up with about the same amount, still the same amount of calls from the service to the database in a very naive implementation. But at this point, you probably have a much more mobile-friendly application. It's only making one call to data and it's getting a much smaller payload for it. And as a bonus, you've got a strong schema that's asking about data you know exists, and you've made, probably made UI developers happier in the process with all these guarantees they've gained. So that's all nice, but let's talk about metrics with GraphQL, because it's not just a GraphQL talk. So once I got to a good understanding of what GraphQL was, I started thinking, I actually see this as a pretty good use case for metrics, because our users fundamentally, they probably have more of the business knowledge to know how to explore the connections between data than we have as server developers. And with GraphQL, it kind of really lets you do that. Like in the example we saw before, I could foresee a way of structuring a query that allows the user to, just keep digging deeper into an object and its relations with no extra development cost to the backend. So maybe it'll save server developer time a little bit. And yeah, so it all sounds good. It sounds like all we have to do is model our business data structures into the schema and figure out how aggregations look, maybe, and the rest should be magic. I don't know. Yeah, when I first was exploring it, I ran into a lot of examples like the one we just saw. A lot of CRUD APIs that were ported over one field at a time, one object at a time. But that's a really easy use case for our metrics API. It wouldn't be worth building if we couldn't allow these clients to have free-form exploration, but on Rails, so they're not abusing it like they would a database they've never used before. What this means also is maybe they want multiple aggregations at different levels of nesting. They might be grouping salespeople by the departments they work at. They might be grouping grouping sales by cars and car brands, by date, and so on and so forth at different levels. And I kind of, as a goal of this experiment, I think it's imperative that we have something that allows for this freeform exploration and aggregating in kind of a really nice way. And for the time series results to be valuable to the product, the server needs to be responsible for joining the raw metrics data with objects that would exist in a more temporal database like Postgres, or whatever you're using. Because if we're using a time series data store, we don't keep a lot of static data in there. We're recording events of sales and whatnot, so we want to be able to reference it back easily without having the UI have to do all these joins again. So I started looking around for guidance if anyone had done this before, and at the time there wasn't a lot of work done in terms of using GraphQL for aggregations. Lately, I've been seeing a lot more questions come up about this use case. But if people are doing it, they're definitely not talking about it. But I think people are starting to realize at the same time that it has a lot of potential in this area. So let's design a query language for our metrics. On the left, we start with basics again. Simple query to get revenue for all sales. On the right, we have what's called the GraphQL schema language, which is shorthand for a GraphQL schema. The queries that are passed from the left by the client are checked against this and validated by the server and the client as well. In the full expansion, each of these fields would usually have a function associated with it, where it would take the result that was evaluated by its parent and parse it into the response at that level, at that field. And in addition, these functions get the arguments that are passed along with the query, along with context, abstract syntax trees, and other fun stuff like that. So now we move on, and we add a date range filter to the query, which is the essential filter for any kind of like time series data store, a time series aggregation. We allow the sales to be filtered by start date and end date, and on the right, I am showing how that query would be updated. We add a new input object for the date filter, and we add the date filter argument to the sales field, and that's about it on that level. And then we also, another way we could keep enhancing it is, previously we would always be getting the sum total of revenue for all of the sales in that period. At this point, you might want to go back and add different kind of statistics that we can ask about revenue. So, like if you've worked with Elasticsearch before, this might look like like an ES mapping with a revenue field as an within a stats aggregation on the revenue field, and at the bottom here on the right, we see that I've defined an enum called stat for the different kinds of statistics that can be asked of this field, and a default value of sum, where if you don't specify one, you're always going to get the sum, which makes sense. Usually, you're trying to get the total over a period of time. So yeah, let's move on to like actual aggregations, because it's just filtering. One very common aggregation is the date ag, where we're trying to break things up by some kind of a value. So yeah, we want to bucket chunks up by a chunk of time, and notice that at this point we're using enum argument rather than a string, which is something that I really like about GraphQL, because typically you would just pass some kind of a string to an API and hope that it is valid. But in this case, we can limit the input values in the schema to hour, day, and month. Say minute aggregations are too expensive for the server to compute. And in this case, if the client chooses to, they can validate the client side and see an error right away that it's an invalid input. And most of the tools for posting GraphQL queries are going to prevent those queries from actually being posted to the server and executed until those queries are valid in the first place. So yeah, the strong typing around this is really nice, and I think whenever you can use enums for this type of arguments, it makes the world a lot safer. So we've done that, but so what if at this point we're getting like daily sales revenue, and what if we wanted to do both daily and monthly sales revenue at the same time? And naive approach might be let's just add another interval. We have one by day, let's add another by hour. But this isn't going to work because if we recall, the response is a JSON object. We can't have two keys in an object with the same value, with the same label. So how do we do this? Well, luckily GraphQL supports something called aliases, where essentially the user specifies exactly the label associated with a field that they're querying, and the response will respect that. So what comes back from the server at this point will be an object containing both daily and monthly, even though they're computing the same kind of aggregation. One of them by day and one of them by month has different parameters. And this translates pretty cleanly to a JSON query, to a JSON response. All right, and the other very common kind of aggregation is when we want to break this data up by a type of object or a field. So we're asking for sales, and we want to group it by the agents that own the sale or the category that the sale falls in. In this case, category will be something like appliances, electronics, accessories. So these different types of objects that may be returned by the grouping have different fields associated with them. So in this case, we make use of the union type of GraphQL, and we define this group aggregation. And we see here that on the agent, we can ask for its specific fields, and if we want to group by category, we can as well. And only if you choose to make these groupings will the server run the resolver function that translates the request into an actual value. So if you leave out category, you can, if you write your server with enough care, you won't ever be grouping things by category. So once we have an example of grouping like this, we might want to move on and group things on more than one level. So it's reasonable to say, like, we want our agent's sales to be, categoried and bucketed into some kind of a date range. And GraphQL actually allows us to create a reference, to have a child object that really is the same object that you're currently on. So we have this category type, and the group field is a union containing a category type. And really the reasoning for that is, if we look at a lot of like threaded discussion kinds of websites, essentially you're posting comments that are responses to another comment that are responses to another comment, and the nesting level might go arbitrarily deep. So it doesn't, having this kind of a representation in your API that is honest to the kind of representation that is ultimately surfaced to the user is really nice. So yeah, they're like going beyond that. I haven't really addressed much the joining side of things, how that might happen. So it's actually, in my opinion, pretty straightforward if you're following this kind of an approach to your query structure. The precondition being that your time series documents should obviously have some kind of a reference back to the Postgres or some other databases object that those things are associated by. So in ES, we have a sales document that contains a mapping to the agent that owns it. So pretty much what we end up doing is turning the filters that are passed as arguments to a field into a query to the backend data store, and evaluating the objects that are associated with that query. From that, we know what IDs there are that the client really wants to know about, and we can apply that as a filter to our data store. So you can keep your time series data store clean, containing only IDs referring back to the temporal objects, the permanent objects configuration, and let the server worry about joining the two values together. So yeah, going back to this diagram, we've done a lot focusing on UI and GraphQL as a service, and optimizing the amount of calls that are happening between those 2 points. But we still have GraphQL, the GraphQL service, making a lot of calls to the database. And the question is, can we reduce those server to database calls? And yeah, there are ways to do it, but they come oftentimes at a cost. And because the GraphQL folks haven't really made very strong opinions about, how the server side of this looks like, there's a lot of different competing approaches to optimizing caching and performance on the server when the server has to run all of these RESTful API calls, all at once. So one thing that I found, that's complexity cost, but it actually works relatively well, is the concept of query execution planning phase. So this is actually something that's an open pull request on GraphQL.js, and something they're very interested in. But the idea, it's not something that's been merged in yet. But the idea is to add another phase to the query resolution, where you have the server looking at the query structure, planning out what it has to do before it actually ends up resolving the query. But one way we can currently make that work before someone decides how to implement it in GraphQL proper is performing a second parsing or hooking into the existing parsing of the abstract syntax tree. So the JS reference library of GraphQL and various other libraries that I've used, like Clojure, actually expose a lot of the tooling necessary to talk to that syntax tree as it's being parsed, and do custom functions, add additional middleware while it's being parsed. So that actually is a really nice way to convert a GraphQL query into a single, or maybe two, if you're doing filtering, backend queries to data stores, where you pretty much create a mapping, a one-to-one mapping of any GraphQL query to, say, a query to ES or any time series arrangement of data. But you end up with definitely a tougher, potentially a tougher upgrade path. I mean, you're not using any private APIs. You're definitely using everything according to spec. But if the spec changes in the future, you have to definitely do more work to perform the upgrades. So yeah, on that aside, see some of it in action. One of these tools that's really nice that I've talked about is graphical. If I click this, hopefully, there we go. And this is actually a public GraphQL API called GraphQL Hub that allows you to query things like Twitter, Hacker News, Giphy in graphical. So I'll just start with an example. Let's go for Giphy. And you notice as I type in, because of that introspective nature of GraphQL, you actually get auto-completion of the things you're able to do. But if you don't know what you're doing here, I can just as easily pull up the docs within this web-based IDE, essentially. See what I want out of Giphy. And we see there's 3 different methods. Probably want to search for what's available. And says what we can look for. So let's do a search, and we're querying for GraphQL, and complete it, and let's just get the URLs. And there we go. Pretty straightforward. Nice thing about it, although like we can't really see it here, is when any component fails, say that the search of Giphy failed, the Twitter search above would still execute because there's no dependency between that tree, between these two different paths of the tree. So you would see errors associated with the search field, and it wouldn't dig any further into evaluating nested objects. But the Twitter field would still resolve properly. And I really like this about GraphQL. It's essentially like with the power of our time-based aggregations, and this, it kind of is an IDE for looking into your like time-based data. A lot of these things can easily be visualized in Vega Lite. If you haven't heard of Vega Lite, it's actually pretty well suited for GraphQL support because you can really get the right format of data in a single query. And what it does is you specify in a JSON structure the actual like definition of your visualization, the data that goes along with it, and some really high-level concepts like describing it as a bar graph or a line graph, and with its data inputs, you end up with a really nice visualization that I'm not sure I can pull up right now. But one thing that I think why this ties into GraphQL really well as well is having the viz alongside data. You could, in essence, take a Vega Lite visualization. Let's see if I can get one up. There we go. And this is actually, if you can zoom in a little bit, this is actually the data returned by our GraphQL call, revenue and date for sales, put in here directly, and we've just defined it as a line with date. This is the entire specification of a visual of this, and we can go in all kinds of different directions with it. And in the future, I think it'd be a good idea to have these be able to specify the viz itself inside of the GraphQL query and get both the representation and the data structure, both the visualization and the data structure of what you're working with in a single call. And go back to this. So yeah, closing thoughts really is that this tech and its use for exploring nested data, while it's really in the early phases right now, we really like what we're seeing. I am looking forward to like where the technology goes from here and what ideas people have for solving these issues. But there's a lot more to GraphQL than has been covered that's actually particularly useful for time series aggregations. One thing in particular being the subscription technology. So GraphQL has a concept of subscription that is a pub sub mechanism for data, and that portion of the GraphQL spec is, while ready, it's actually seeing a lot of tooling and a lot of action happening right now. And from here on out, that's probably going to be kind of a game changer for getting pub sub out in a lot of places. And GraphQL itself, like even if you aren't fully like bought in on it for like time series data, the tooling that it provides is something that I'd really like to start seeing in a lot of different APIs, even if they're not necessarily something on top of GraphQL. Like we have Swagger, but Graphical goes so much farther than Swagger did. And as a technology, it's really starting to take off with GitHub like releasing its new API exclusively. with this technology. And that's primarily it from my point of view. But any questions you'd like to ask, feel free to ask. Yeah.
So I don't know if you said that. This GraphQL, is it like a layer in front of your service? You deploy them like together, or how does GraphQL get?
Great.
Question a bit too.
Sure. So the question was, is GraphQL a layer on top of your services? Do you deploy it together with your services, and how do they interact? And so the GraphQL itself, you bring up a GraphQL server that serves the schema for the GraphQL query, and clients post their queries to this server. And whether you choose to tie in your services into that server or have it call out to different APIs, that's kind of like up to your implementation. It just provides you with a way to attach functions to different components of that schema, and in those functions you could be, calling other services or implementing your whole entire application.
So if you were looking for sales data,
yeah,
yeah, GraphQL would go on the REST call to the existing sales endpoint.
Yes, it could be doing that.
Or could it like talk directly, skip over that REST API?
That has been my implementation so far. I don't use an existing REST API. I take a look at the query that's presented, figure out what objects I'm dealing with, query the databases directly, and define the aggregations that are available. So yeah, you can skip the whole layer of calling additional APIs and have it all happen right there.
Can you restrict on the client side what they can actually do, or something like that? Like, obviously, you want to have the output queries too, indexes, and all that other stuff to go on with this client. Crazy queries.
Yeah.
How do you manage some of that?
Yeah, a lot of that trick is in that schema design, really. There's no reason that your schema needs to be very low level to expose what indices are being hit and all the fields that are available on that index. You can present a very high level view of the world to the client to only talk about very high level business objects and do all of the querying on the back end. Yeah.
So what were some of the difficulties in getting it up and running? You mentioned that it was early on.
So actually the biggest difficulty was a lot of the unknown of how it really works with aggregated data. Everyone has been using it for getting an object, getting its fields, doing some filters, and that's it. I was really trying to vet it to see if it really does work for being able to cut data in different ways. That was one big challenge. Even the other big challenge was server optimization. I didn't want to be making a different query to the server for every layer, a different query to the database for every layer of the query, which that's pretty much the RESTful world, and it's a direct translation of that. But I went back and started taking a look at the AST and converting that into a standard representation of constraints for Elasticsearch, for other databases, and then the resolver would take a look at that representation and understand how to perform at most 2 queries and join the data together. The really nice thing about, I keep talking about ES, but it's because we've been using ES a lot as a time series store. The way that ES structures its aggregations mirrors a lot with how this structure of GraphQL queries is. When I add another alias there, I can request to get that same exact aggregation with that same exact label back from ES, and it's a very simple translation from one to the other. And likewise, ES also allows you to do nesting of arbitrary levels. But yeah, doing that translation was challenging, and really it's just kind of new ground. Yeah, it wasn't until months after I'd done this that I first started hearing people asking about how this can be done. Elasticsearch.
So I was going to ask you, contrast compare Elasticsearch aggregation with what you're doing here. But
yeah.
So is this working on top of that? Is that what would you throw into an ES paired with aggregation versus using this?
Sorry, can you repeat that?
So compare and contrast what you get with Elasticsearch aggregation.
Okay.
Versus what you use this method.
Yeah.
For, right?
So yeah, comparing and contrasting what we're getting already with Elasticsearch aggregations and this approach, which is a little bit of a translation on top of them. The number one biggest gain is joins of data, because Elasticsearch alone, if it's using a time-based index, you see the world as it was at a specific period of time. But if you're joining sales to an agent, and there was a misspelling at the time the agent was added to the database, you don't want the misspelled version of the agent. You don't want to group by that. All you really need is that ID, and you want to do the join and bring it into your time series data. So with ES, you don't get those joins at all, and this is like a really nice vehicle for that. And second, it is a subset of what ES does in a lot of ways, but that itself is a nice thing that you get on top of it. If you're exposing something to UIs, you can limit what relations and what groupings should be available to any kind of document. Whereas if a user has never used ES before, may think different doc types and fields are related when they really aren't, and perform aggregations that are way too heavy to execute.
It seems like the aggregations are the new piece here. So
yeah.
Can you use the aggregated data as a category in the query? So, for example, can you take a histogram and based on the top 10% slice that sort of a having number bigger than?
Yeah. So the question is, can you use the aggregated data that you get at one point, and from that use that for another aggregation, or get from that, like, understand what the top 10% of users are. With GraphQL, yes, there is a way. There are bindings that you can assign from one piece of the tree to another, and GraphQL will take what is returned from. It will execute the query. It will execute each piece of the query in the right order in terms of like what depends on what. I wish I had an example of this right now, but you can pretty much designate a chunk of the query and say, I want to use whatever value is in here in this completely other part of the tree for a filter or for an argument.
Can we keep a custom client-specific queries in the server?
Yes, the server gets the whole query, and that's probably a nice way to do caching as well, because if you know your data will always be the same for a query, you can store it on the server. You can just, another thing that I've seen used is a hash is returned back to the client, and the client just has already designated what parts of the query will change. You can label variables in GraphQL, and just you pass a JSON object containing those variables and the query that it's going to be associated to. And the server will be like, okay, I've seen this query before. I don't need to parse it again. Just like run it again with these variables.
So with your server optimization, how much performance gain do you see?
Hard to measure. It's absolutely a gain because in the previous.
Seeing some performance problems that prompted you to try to optimize it?
Yeah. Well, really, I was actually guarding against the possibility of like having a lot of queries being executed against ES data. By doing the server optimization, I was able to carry down the tree, the context of really like the biggest reason is limiting the subset of data that the aggregations run over. Previously, if in a lot of our existing applications, clients would request all of the data, all of the aggregations, and then do the slimming down application side. And with the optimizations, if we look at that query first, that filtering that's happening at the top, and turn that into a list of data, a list of IDs, and then turn those list of IDs into a filter for ES, we can limit the calls to ES and the data it works over in one swoop. But I will say overall, I saw a great gain from that. I did not see a huge gain from going from having multiple queries to ES that are properly structured to having one with deeply nested aggregations. For the most part, if you're doing 5 queries to ES, each with a different aggregation, or 1 query to ES with a deeply nested one, there's not a huge difference because ES is just going to be working a lot longer on that one query. And it's more likely to say, I've worked too long, I'm going to crash now. Whereas with this, if you're working with individual parts, at least you'll have a partially, complete data.
Well, it's Elasticsearch, it bounces back.
Yeah. All right.
All right, thanks, Boris. That was great.
Good.